Hello, everybody. Welcome back to the Casual AI Talk series for day 4 of this series. As I hinted to in day 3, today we're going to be talking about pre-training on massive corpora and how that leads to getting these so-called foundation models. So it's what we're going to be talking about is one of the major aspects that allows modern LLMs to become what they are, and I'm going to be referring to pre-training a lot in this video, and that's essentially the idea of training these models on a large amount of data prior to them becoming more specialized through a process called fine-tuning. And we'll get into task-specific fine-tuning in some of the later episodes. But today we're going to be talking about where modern models learn general language patterns and essentially the general capabilities they have. This also leads into the how of how they know things, without us giving them any guidance or very minimal guidance. So this whole idea of pre-training is what we refer to as self-supervised. So the model learns by predicting specific parts of the text, and these parts of the text are inherent to the text itself. So it's really easy to train these models. So no manual labeling is required, as similar to the tasks like classification, where you actually need explicit labels. Here you don't need explicit labels. So there are two classic objectives that dominate this field of language modeling. So the first type is masked language modeling, and the second one is causal language modeling, and we'll go over those. So the idea of masked language modeling originates from this model, which is called BERT, and the idea is to hide like a certain portion, let's say like 15% of the tokens, so spans of text in the middle of the text, and train the model to recover that masked portion of the text, so the part of the text that you removed, using the text that came before it and the text that comes after it. So the other way of doing this is causal language modeling, which is actually the way that the GPT family of models does this, is to predict the next token given the previous tokens. So when you have a sequence of text and your mask is essentially on the remaining part of the text, and in each iteration you're trying to figure out the next token that you want to predict. These simple games, if you're gonna call them like that, for the model forces this internal representation of the models to internalize the syntax, the semantics, and the facts spread across these huge amounts of text. So let's go a bit more into detail about the two models that I mentioned, so BERT and GPT. So BERT was introduced in 2018 and is what we refer to as a bidirectional encoder. And now you know what an encoder is if you've watched day 3. So it's a bidirectional encoder. So it's attending to both parts of the text, so the prefix and the suffix of the masked portion of the text. And the idea is to predict the next sentence. It was originally trained on the English Wikipedia and a dataset called the book corpus, which is a large collection of books. So the combination of the bidirectional context and the broad text made BERT a rather, let's call it versatile feature extractor. So it was commonly used for tasks like classification, question answering, and a couple more tasks back in the day. And there are even like derivatives of BERT models that are still being used to this day. And the other type of models are the GPT-style models, which are decoder-only transformers. And again, if you watch day 3, you know what decoders are. And they're trained to essentially predict the next token across web-scale texts. And GPT-3, which I mentioned in the first episode, was famously was trained on filtered common crawl data, and it used like a very specific data set of web text. There were like two data sets about books, I think book corpus and one else, and it was Wikipedia, and it gave the model a very broad knowledge base, and it was pretty good at doing zero and few shot learning. And if you think about it, it was a really good model even by modern day standards. So these models are trained on a lot of text. I mean, we glimpsed past it, but when I say Wikipedia, I mean like the entire knowledge base of Wikipedia, and you can imagine that's a lot of data. But it's not just about having a lot of text. It's also about carefully filtering the data that you have. So a very important example in this idea of filtering was the T5 models by Google, which was trained on the C4 data set. And what was C4 again? It was something like colossally... Oh, wait, so this is going back into my memory. So like colossally cleaned... I think CC stood for common crawl, or common crawl. So it was like a clean version of the common crawl data set, which was essentially designed to only have high quality data, with like a lot of boilerplate and like generated files removed. Like it basically removed as much as non-English text as possible. It removed low quality text. I don't remember what exactly they define as low quality text. And what I remember from that, it was that they show that so that like both the scale and the data have a very big impact on the capabilities of these models. So the filtering of data can have a huge impact on the quality of the eventual models. And if we're thinking about it, and also like in the context of code models, naturally, it's just not only natural language and these data sets that we're looking at, right? So code models are pre-trained on, hopefully, you would hope, permissively licensed code. So they would learn the APIs, the language idioms, and the patterns across all these different programming languages. And a very famous example of this is the Big Code project, which they have this data set called the Stack, and there are two versions of it, which are is like a data set of terabytes and terabytes of data, and based on this data set, you have the star coder family of models, which are really good examples of how you can deal with this type of data responsibly, and like they have very cool ways of opting out for your data being used when training these models. And the models are actually pretty good in terms of code generation, are being used in open source projects. So I would, if you're interested in this type of stuff, I would definitely recommend this data set and model. And okay, so we have this type of data and we have these large amount of data, but why does pre-training matter so much? So pre-training essentially shines because of something we refer to as scaling laws. So if you increase model size, the data set size, and you increase naturally the compute required, a language modeling loss improves semi-predictably. A lot of people would say predictably, but it's rather semi-predictably when you're looking on a big order of magnitude. Bigger models trained on more data, they do still memorize, but they don't only memorize, they also learn from these. So they become transfer learners. So they learn these ideas underlying the actual patterns that they're learning. So there's this body of work that follows on this idea of scaling laws, and they're referred to as chinchilla scaling. So this paper showed that many language models, like at the time, were undertrained for their size. So they showed that given fixed compute, it's better to actually increase training tokens roughly proportional to the increase in the parameters of the models. So essentially, for a given budget, training longer on more data can be just making models bigger. That's essentially what they show. And the nice part about this is when you train on these large amounts of data for relatively good amounts of time, you get something we refer to as emergent capabilities. And what that's saying is that when the scale of your models crosses a certain threshold, models start to exhibit certain capabilities, like in-context learning, that weren't present in like smaller, less trained models. And essentially, they're no longer naively predicting next tokens, but they're actually trying to convey meaning, and they're trying to achieve a certain task. And that's the idea of why these models are getting so good. So I talked about why these models are getting good, and with these foundation models, as they call them. So the foundation models are models that are trained on these large amounts of data, and just by laws of probability, there are going to be a huge amount of diverse sources in there. So like encyclopedias, books, forums, documentations for, I don't know, different libraries you use on a day-to-day basis. And these models start to capture their grammar, meanings, the underlying patterns that are used. And that's why these general purpose models, so a single model pre-trained on these huge amounts of data, can, even without fine-tuning, perform a lot of these downstream tasks. And we commonly refer to these models as foundation models. So they're foundationally able to solve a lot of tasks. And here I want to point towards something that's kind of overlooked in my opinion. Pre-training on a lot of data is nice and all, but you also have to deal with a lot of risks that you're bringing into your pipeline. So you can have a lot of biases in your data. You can have a lot of, if you're training on not a carefully curated data set, you can encourage memorization in your models. You could be possibly using non-permissively licensed code, and that can pose a lot of problems. And that's why data governance and ensuring that the data that you're using is permissively licensed and that your data is properly filtered is really important, even now, when actually more so now that we're training all these models on all this amount of data without with in a lot of cases not really giving it the enough care as it needs. So it's really important to be aware of the societal impacts that these models are having, and the potential they have for example, misuse. And we know like that these models require a lot of computational power. So if you don't need your model to be 200 million parameters, or 200 billion parameters, and trained on gazillion trillion bytes of code, you should probably just stick with like a pre-trained model, and they perform pretty well. But of course, who am I to tell you? You know better what you should be doing. Today we talked about foundation models and how scaling laws work a bit, what pre-training on large corpora of data entails, and what the consequences are. Stick around until the next episode, where we'll talk about a new aspect of the LLMs and AI, and with a focus on AI for SE. Thank you for your attention, and I hope to see you next time. Bye.